scientists have unearthed compelling evidence suggesting that the Martian crust harbors enough water to potentially fill entire oceans.
When NASA's Perseverance rover drilled into the rocky Martian surface near the edge of the ancient river delta in Jezero crater, the initial goal was simple but historic: search for signs of ancient microbial life. As it descended through layer after layer of sedimentary rock, each one representing thousands or millions of years of Martian history, the rover encountered something utterly unexpected, something that could shift our understanding of Mars and even our place in the cosmos. What began as a mission rooted in science quickly transformed into one that dances on the edge of revelation. The Martian soil gave up a secret it had held for eons. Before we start, smash the like and subscribe buttons for more updates. In a stratum of rock dating back 3.6 billion years, Perseverance detected an unusual series of isotopic ratios in carbon compounds, ratios that are impossible to form through known non-biological processes. These were not the faint hints or chemical shadows of once-living organisms that scientists had debated in the past. These were unmistakable biosignatures, structurally similar to those produced by Earth-based life forms. Compounds rich in carbon-12, with trace amounts of specific amino acids, revealed a fingerprint so distinct, so finely tuned, that it ruled out contamination, photochemistry, or volcanic origins. This discovery wasn't simply intriguing, it was earth-shaking. The implications of this chemical signature go beyond the question of whether life once existed on Mars. The configuration and complexity of the molecules suggest not just primitive life, but the presence of a microbial ecosystem that endured over a long geological time frame. The layering in the sediment implies cycles: wet and dry, warm and cold, oxidizing and reducing, conditions that mirror Earth's own evolutionary crucibles. The Martian biosphere might have gone extinct eons ago, but it left behind a chemical manuscript carved into rock, awaiting the tools and eyes to understand it. Perseverance's sample cache system confirmed the uniformity of these biosignatures across multiple rock samples taken from different depths and locations in the crater. This ruled out a localized anomaly or a rare geochemical oddity. The same patterns repeated, like echoes of an ancient Martian chorus, offering consistency that underscored the biological origin. What's even more startling is the diversity of the molecules found. Not limited to a few types of amino acids, the samples included complex chains that imply not only the existence of life, but its potential adaptability and evolution over time. The data sent back to Earth was so dramatic that it triggered emergency closed-door meetings within NASA and among international space agencies. There was no precedent for this. No training manual, no press template. The robotic arm of a distant rover had just reached across 140 million miles and shaken the foundations of biology, philosophy, and theology. In response, a new branch of astrobiology was proposed almost overnight. Previously, theoretical models of alien biochemistry were re-evaluated in the face of this raw, undeniable evidence. The scientific community was jolted into a frenzy of re-evaluation. Suddenly, Mars wasn't merely a relic of a failed planet, it was a sibling world, one that may have nurtured life parallel to Earth's development. The likelihood that life originated independently in two separate solar system bodies casts serious doubt on the idea that Earth is uniquely privileged. If it happened twice here, it likely happened countless times elsewhere. The famous Drake equation, long used to estimate the number of advanced civilizations in the galaxy, suddenly needed revision, not in theory, but in numerical certainty. And yet it wasn't just science that stood at the edge of transformation. The cultural, philosophical, and existential ripples extended far beyond research labs and mission control rooms. The notion that life, real, tangible, organic life, once thrived in Martian lakes and perhaps even rivers forced humanity to reckon with new possibilities. Religious ideologies found themselves confronting a broader creation story. Age-old questions about existence, purpose, and solitude took on new dimensions. Humanity was no longer the only known expression of life in the universe, not even within its own planetary neighborhood. The geological setting of Jezero crater became the focus of international interest. Once thought to be merely an ancient lakebed, it now resembled a paleontological treasure trove on another world. Scientists speculated whether Mars might have experienced a more complex climate history than previously believed. The alternating clay and sulfate deposits suggest periods of stability followed by harsh transitions, much like Earth's own glacial epochs. Within that variability, life found a way to emerge, or perhaps it was seeded there. Among the more unsettling aspects of the discovery were certain similarities to extremophiles found on Earth, organisms capable of surviving in harsh, acidic, or radioactive environments. Some of the compounds resembled biosignatures created by thermophilic bacteria near Earth's deep-sea hydrothermal vents. If Martian life evolved in such niches, it raises the possibility that life began not in pleasant Earth-like conditions, but in the hostile embrace of energy-rich environments. This, in turn, led researchers to consider that life could be far more resilient than previously believed. The traditional constraints placed around what constitutes a habitable zone, such as the Goldilocks conditions around a star, now seemed limited and outdated. Perhaps the most chilling realization came from the mapping of the Martian biosignatures to patterns that suggested evolution, adaptation, and eventually decline. There was no abrupt halt, no planetary extinction-level event etched into the stone. Instead, it appeared that Mars gradually dried out and cooled, and with it, life faded. Not with a bang, but with a prolonged sigh. The idea that an entire biosphere could wink out simply because a planet became less hospitable hit close to home. Earth too faces environmental tipping points. Mars became a warning as much as a revelation. While the immediate implications dominated headlines and academic circles, deeper discussions emerged within the corridors of space policy and planetary protection protocols. If Mars once hosted life, even if extinct, how should humanity proceed? The very act of exploring the red planet might endanger its remaining biosignatures, or worse, disturb dormant microbial life. Could humanity inadvertently revive something long buried? Or through exploration, unintentionally alter Mars's fragile ecological remnants? Yet fear was not the dominant emotion, wonder was. The discovery reinvigorated dreams of space exploration. Public interest in Mars surged to heights unseen since the Apollo era. Funding proposals for missions to retrieve the Perseverance samples were fast-tracked. Plans to send human missions to Mars in the coming decades were no longer justified by curiosity alone, but by the weight of history. A race to uncover more Martian life, or its fossils, began in earnest. Suddenly, every Mars lander and orbiter became part of a grander narrative. Instruments originally designed for geology were repurposed for biology. Past missions were reanalyzed through this new lens. Could Viking in 1976 have detected life but misinterpreted it? Could Opportunity and Curiosity's ambiguous organic molecule detections have been early tremors before this seismic revelation? In hindsight, the data spoke a clearer language. New questions sprang from the old. If life evolved on Mars and died, what caused its extinction? Was it purely environmental, or did a catastrophic event play a role? Was Mars ever more Earth-like? And could its fate mirror our own? Researchers pondered whether life on Earth might share an ancestral origin with Martian life. Meteorites blasted from Mars have landed on Earth, and vice versa. Could panspermia, the hypothesis that life spreads between planets, be more than a theory? There was a humbling effect in recognizing that the universe may be teeming with life, but not necessarily with civilizations. Mars suggested that life can start and thrive, but survival depends on planetary fate. Intelligence, it seems, is not a guaranteed outcome. In the fossilized traces of Martian microbes lay the possibility that Earth's own path is an exception, a rare and fragile gift that must not be squandered. With this discovery, every icy moon and exoplanet rich in water or carbon became suspect, not of lifelessness, but of secret abundance. The search for life in Enceladus's plumes, Europa's ocean, or the methane-rich air of Titan took on new urgency. The cosmos no longer seemed like an empty stage awaiting actors. Instead, it felt like a vast archipelago of stories waiting to be read. Even more, this revelation rewired humanity's future vision. Mars was no longer just a barren rock to be terraformed or mined. It was a sacred archive. The idea of settling the red planet transformed from conquest to stewardship. Colonization gave way to conservation. For the first time, humanity approached another world not with dominance in mind, but with reverence. The voice of another biosphere, even if long silent, demanded to be heard. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, What are your thoughts on NASA's Mars discovery? Do you think it changes everything? We want to hear from you. Thank you for watching, and see you next time.